Okay, I want to do something a little bit different this morning, and I apologize for the delay in getting started here. But we're covering Section 8, pressure sensors, and I went through a lot of my video uploads and I pulled out some pictures from the case studies that I have to help emphasize this topic. So, real quick, I guess we could start here. Let me go to this and talk about my channel page for a second so we all understand where to find this playlist. And that would be if you go to my channel page, make sure you're not on. See, I don't know how it looks for you guys, but if you go on my channel page, on the main page, you'll find the different chapters that are in my book. This is where we are. Chapter 1, Chapter 2, Chapter 3, and so on. Down here, Chapter 8, I have listed under how to troubleshoot computer input problems, MAP, ECT, TPS. So that's where I went. Chapter 8, and then the next page should be my playlist that I have set up for pressure sensors. You see I have a power steering pressure sensor, MAP sensor, a Ford DPFE. There's a few DPFE sensors. That's delta pressure feedback. It's an EGR pressure sensor. And looks like that's it. Oh, there's a GM tank pressure sensor too. So again, as we've gone through potentiometers and how common they are, and if you know how to check a TPS in detail, you know how to check every other potentiometer. We're in the same boat with MAP sensors. Our focus is the MAP sensor. Let me teach you about the MAP, how it operates on the vehicle, and then we'll plug in all the tests for every other pressure sensor. It's all the same. Okay? So, again, pressure sensors is where we are. We'll do this part briefly. I just need you to understand what the MAP sensor is used for, and then we'll talk about the testing part here in a minute. So just like Section 7, potentiometers was the title, but then we went right into the TPS. Same way for Section 8. Pressure sensors is the title. We're jumping right into the MAP sensor. And again, testing will be the same for all pressure sensors. Our focus with engine performance, of course, is going to be the MAP sensor. So let's talk about this MAP sensor for a second. It is for a speed density engine. First time maybe you've heard that term, I'm not sure. No, we talked about it in Section 1 when I taught you guys the difference between a MAP and mass airflow engine with a vacuum leak. Do you guys remember that discussion? I said that a MAP engine technically is called a speed density engine. It's a mathematical formula used to calculate airflow. This right here would be your speed density formula. The manufacturer calculates intake air and EGR flow and throttle angle and volumetric efficiency combined with the MAP, and it says we have this much airflow entering the engine. So MAP is our main input for speed density. It measures manifold pressure. Pressure and vacuum are opposite. We tend to think about vacuum as a suction, and it's really not the case. It's just the absence of pressure, and it's atmospheric air that's forcing that to happen. It's not really a suction. Okay? With the MAP sensor being the critical player, and I missed this part. I'm not talking about an engine with a mass airflow sensor. We just have a MAP. Okay? The MAP is really the most important sensor we've talked about so far. More important than engine coolant, more important than throttle angle, more important, of course, than the intake air. This MAP sensor is used pretty much all the time as far as how much air is entering this engine. Airflow into that engine and air pressure in the manifold or vacuum in the manifold go hand in hand. And so if we have low vacuum, which would be a high pressure, this part's difficult for me because I always bounce back and forth between the pressure and the vacuum. It's probably better if I just talk about the vacuum because that's what we're all used to hearing. If your vacuum is low in an intake manifold, let me rephrase that. When would your vacuum be low in an intake manifold? Low vacuum. What's that? Okay, outside of problems, good point, Robert. Outside of problems, when would our vacuum normally be low in an intake manifold? Opposite of idle. Idle is when we have high vacuum. Throttle plate's closed, pistons are moving, we're trying to draw air in, it's being restricted. We create a vacuum from that closed throttle plate.
So wide open throttle.
Very good. Wide open throttle, we would have low engine vacuum. Or as we accelerate, as we go under load, we have low engine vacuum. So that would make sense that we would have a heavy load and the computer would add more fuel, right? Map sensor, critical play. When do we have high vacuum? Idle would be, believe it or not the highest, but one of the highest levels of vacuum would be at idle. Decel, very good, Robert. Decel would be my highest vacuum because the throttle plate is closed, same position as it would be at idle. What's the difference? RPM would be very high. Pistons are moving a lot faster. There's more of a, if you want to call it, more of a suction effect taking place. So maybe at idle, you might see, 17 to 21 would be normal idle vacuum. You might see as high as 25 inches of vacuum during a decel event off of a map sensor. So let me pause here for a second and show you my first picture that I pulled up. I had a vehicle that has an issue with the map sensor. And where I want you guys to focus would be on this picture right here. This bottom right picture. Let me change that ink so you can see that. This bottom right picture is where I want our focus to be. The car is idling right here. At this point, we have an idle condition. And what I'm doing is I'm doing wide open throttle snaps. Okay? After a wide open throttle snap, would you agree with me that the RPM would be high still at that point up here? That my RPM would still be very high. Pedals to the floor, you see the map voltage rise, absence of vacuum, voltage is rising, or you could say increase in pressure equals an increase in voltage. I think I say that in here somewhere, right? Next page maybe? Yes. High pressure, high voltage, low pressure, low voltage. So back to my map picture. That one. Notice as my pressure is increasing or vacuum decreasing, what's the voltage doing on the map sensor? It's reacting accordingly, correct? So how's the map sensor look so far? Low. We got low voltage at idle, and we have high voltage at wide open throttle. There's something wrong with this map sensor though. Can you pick it out? As we just discussed the decel vacuum, we said decel, you might see during a decel event, we might see 25 inches, where at idle, we would be 17 to 21. This is the idle vacuum. Where is my decel vacuum? You guys follow? There is a problem here. What should that look like during that event? Oh, by the way, there were no codes on this car. This was a 2000, no, that's not it. Yeah, 2000 Grand Am, no fault codes. This is what it should look like. Bottom right picture. Oh, scratch that ink. Bottom right picture. This is what it should look like. This is idle. What's this right here? That's wide open throttle. And notice that voltage dip. Would make sense. Higher vacuum is what? I'm having trouble with my icons here. Hang on. What we say? Higher vacuum. So high vacuum is what? Low voltage on a map. Are we seeing that here? Is my decel vacuum higher than it is at idle? Yes. Are we seeing a lower voltage? Yes. What's wrong with this car? What did I do before and after? What do you guys think? Any thoughts before I show you what's wrong with it?
Sensor dirty.
Good question. Is the sensor dirty? Mass airflow sensors get dirty, MAP sensors do not. Could the sensor be contaminated internally somehow? Of course, but can I do anything about it on a pressure sensor? I cannot. What do you think? What else? Good thought. There's no wrong answer. I promise I won't make fun of you for whatever you say. Robert, any thoughts? You've been on, man.
Boobies.
What's that?
I like boobies.
You like boobies.
You're cool.
That is on recording, and I'll probably leave that too. Robert is the guy who was rubbing his nipples in one of my previous videos. This may be here forever. I don't know. We'll see. Depends if I feel like editing. And I'm thinking no, so I'm gonna leave it. Thank you. No, it's not that. It's not that. But watch. Let me show you some pictures. This will make sense. This is my MAP sensor in this image. Looking right here in this area is the connector. We can't really see the MAP sensor very well. Trust me, that's the sensor for the MAP. And then the vacuum hose is right here. So let's focus. This is where our focus needs to be, is on this vacuum hose. Okay. So check out the next image.
Split.
Believe it or not, it's not split. It looks like a crack developing in there. There was no leak on this hose to the MAP sensor. That's pretty cool, isn't it? That hose was getting pulled in, right? So what happens is we're trapping vacuum up in here. That would make sense then during a snap throttle when we lose our vacuum in the engine. Our vacuum levels would be changing very drastically. Come on, help me out here, Hank. It gets silly sometimes. Vacuum levels, come on. Vacuum levels in the intake would be changing rapidly, but we would be trapping vacuum up at the MAP sensor. Does that make sense then that during a decel, when I should have this reaction of a very high vacuum, that we have some trapped stored vacuum in the MAP sensor itself? It should. This is what's going on with this car. It wasn't just a decel problem though, wouldn't you agree? As you try to accelerate, what should be changing very rapidly at the MAP sensor? If you accelerate and we drop manifold pressure, shouldn't that same drop in pressure also come up to the MAP sensor and tell the computer we have a higher load condition taking place? What's the computer's reaction? Add fuel. How do you think this car ran? I'm pretty sure it was towed in. That's how bad it ran. It would not accelerate at all. Does that make sense? How important is the MAP sensor vacuum hose? It's pretty important, isn't it? All right, what else do we see? These are just some other captures. Same bottom right pictures where you're looking. That's snap throttle with the MAP with the messed up hose. Snap throttle on the MAP with a good signal. This is what we want to see, especially those lower signals. Right, that's a good one there. Those are good ones. That's a bad one. Bottom right still where we're looking. There were no trouble codes apparently. Same Grand Am, right? 2000 Grand Am. Looking down here at the just above, right? These forward and backward buttons right above that. 2000 Grand Am. I did have some codes as far as last test fail. These were it. This is all I had. O2 bank 1 sensor 2 lean, O2 signal low, bank 1 sensor 2, O2 heater circuit. So we had an O2 fault. These had nothing to do with the problem on the car. I took these captures just to really emphasize how difficult our job can be sometimes. You know, we have a fault code that had nothing to do with the car's running condition at all. It was ultimately a vacuum hose problem on the map sensor. Okay? Back to my text for a minute. Something else a map sensor is used for is our atmospheric pressure sensor. It's called a baro sensor, barometric pressure. This map sensor can be used as a baro in two operating conditions. You guys need to remember this. You will see this on your test. It's worded like this. What two times, something like this. What are the two engine operating parameters or times that we can use a map as a baro? And the answer is, think about this for a second, it should make sense. Initial key on and wide open throttle. What would be unique to those two conditions? When we first turn the key on, what's the pressure in the manifold compared to wide open throttle? What's the pressure in the manifold? Any thoughts?
High.
What'd you say?
I said high.
High, yes. Our pressure in the manifold would be high. It would be atmospheric. When I first turn the key on, the engine's not running. That's not a perfectly sealed system. Air is going to come through the throttle plate area idle air control valve when you shut the car off. So we have atmospheric air in the manifold, and then wide open throttle would be the other time. Guys, this is important to have a update on the baro at wide open throttle when you're driving through the plain states and you're climbing the Rockies. We need an update. When does that update occur? Wide open throttle. Okay? So most cars, guys, do not have separate baro sensors. There are some that do, but for the most part, your map is your baro sensor. Something else you want to remember would be the higher in altitude we go, the less atmospheric pressure there is, which means what about fuel delivery? Do we need more or less? If there's less atmospheric pressure, the engine's not breathing the same amount of air, where are we at with fuel? More or less? Less air would be less fuel. Less fuel needed under all conditions. Something else we can use a map for would be for EGR flow monitoring. This picture over to the right is showing us that. It's pretty basic. Notice with the RPM dropping, what are we doing? What's the engine doing? Are we accelerating or decelerating if RPM is dropping? Decel, right? Decelerating. So what would manifold vacuum be during a decel? We just learned it. It would be what? Very high vacuum during a decel. So what the computer will do on a lot of our systems, it'll take that EGR valve that was closed, throttle plate's closed too, decelerating. It'll take the EGR that was closed and it will momentarily open it. Shouldn't we get a rise in manifold pressure if we have good flow through that EGR system? The answer is yes. Why do we see map voltage being low here and then rising? Because map voltage rises with pressure. And then the computer shuts the EGR valve off. It'll close it. And what happens to pressure again? It drops. This is all during a decel event. Guys, this is your OBD2 trip monitor of the EGR system using a map sensor. It's pretty cool. That is our flow test. Now you might be thinking, well wait, you're flooding the manifold with exhaust gas. Isn't that going to cause a drivability problem? You guys remember our discussion with decel events? That during a decel, it doesn't matter what the computer's doing with injection pulse or air-fuel ratio because we're not using the engine to create power. We're actually using the rear wheels are actually driving the engine at that point in time. We're decelerating. When we talked about throttle position sensors, I said we shut the injectors off completely. It doesn't matter what we do to that air-fuel ratio during that event. So it can be used for EGR flow monitoring, and of course spark timing is involved too. We actually covered this page with our last case study, right? How critical is the hose condition? What do you guys think? It's pretty critical. You know, they started putting these map sensors and directly mounting them on the manifold, so there's no hose anymore. The intake manifold would be here, and then they would put a grommet here to seal it. And I used to think it was to get rid of the hose because the hose was a big problem, but it actually wasn't for that. It was for sensitivity and the map reaction, to make sure we're getting a good reaction on that map sensor, no delay with changes in manifold pressure. To emphasize that, take a look at my Hummer series, where I'm using the map sensor to identify intake manifold pressure changes, where I've identified a valve problem using the map sensor, and how important it was that I used a real short hose going to the manifold when I did those tests. I think that emphasizes really why the manufacturers have gone to no hose anymore, directly mounting the map onto the intake. Guys, Chrysler still primarily uses speed density systems, which means what? If I said that's a speed density engine, what would you say? There is no what? There is no mass airflow sensor. A speed density system, there's no mass airflow sensor. See, a lot of people will say there's two systems. There's mass airflow and then there's MAP. You can say that. I say it myself. That's a MAP engine. That's a mass airflow engine. A MAP engine is a speed density engine. Will we see MAP sensors on mass airflow systems? Yes. But is the MAP sensor the same big time player on that system? The answer is no. The mass airflow is. The MAP sensor on those systems is primarily used for backup and for EGR flow monitoring. You'll still see them. So testing this, guys, I'm going to skip this page. I'll just mention it briefly. All I'm showing here is the MAP sensor is more critical than the TPS. And we've talked about the TPS already. We go back to section 7, and if you remember, I talked about throttle angle really not being as critical as some of these other sensors. So this picture, I'm just illustrating the same throttle angle, the red trace at a 0.5 volt in both pictures. I'm doing a in park with the throttle angle at a 0.5 volt, and then in gear with the throttle angle at 0.5 volt. And you can see the big difference in pulse width, which is based off the MAP sensor. That's what that picture's showing. Moving on. The operation of this, I really don't care. I used to try to explain the internals of this MAP sensor until I started seeing some pictures of the inside of these things, and I can't do it. These things are really miniature little processors. And this one's showing like a flexible silicon diaphragm and whatever. But when you think of these circuits, you can actually think of it like this. When you're testing them, there is nothing wrong with thinking of this circuit how I just drew it. What is that a picture of? We just covered it. Section 7. Title of Section 7 is what? TPS, potentiometers. It looks like a potentiometer. In your mind, when you're testing these, you're thinking potentiometer. Just know there's no movable part in there. And that pressure change the voltage signal. But think about it like that when we're doing our test. Check out the wiring. Isn't the wiring exactly the same as a TPS? 5 volt ref, signal and a ground. There's some calibration differences. What's an NA engine? You guys that play Gran Turismo should know this. Anyone? NA. Yep, naturally aspirated. Then we got our turbo engine. So we have a turbo engine with a MAP sensor. They're calibrated differently than an NA engine would be. Should make sense. Key on, engine off, wide open throttle would be the same on an NA engine, right? Be the same pressure with just the key on, atmospheric pressure. wide open throttle, atmospheric pressure. It's not like that on a turbo engine. Key on, engine off would not be the same as wide open throttle because we have boost pressure above atmospheric. So these things have to be calibrated differently. So that's all that illustration is showing us. And I'm giving you a typical range. What we look for, that checklist I've been talking about. What's our checklist? ECT, IAT, TPS. We actually did it yesterday on a Honda we had in here with an idle surge. We looked at the coolant sensor first. Why? Because we had a fault code for it. Well, we didn't know the guy was unplugging things, but we went through this checklist real quick. Okay, ECT, good. By doing a simple voltage check, we had numbers in our head. We said, okay, we actually had a little help. It said 3.2 volts cold, and what was it? 0.6 hot, if I remember. And we read 1.5 volts. Okay, check mark. Next, TPS. How did it look? Under a volt, 0.39. Did a sweep test, looked good, check mark, off the list. Next one, map. How's the map? We didn't get that far on that Honda, we didn't need to, but this is what I'm thinking about when I'm thinking about map sensors. Is 0.5 to, now that's really not accurate, that's what I wrote here. I'm actually thinking about 1.5 to 4.5 volts is what I typically see on a map. This 1.5 volt signal would be idle. And this 4.5 volt would be key on, engine off, or wide open throttle. So this one's a little different than a TPS. If it's a TPS, you turn the key on, you do your idle reading, and then you do your sweep test. But for a map, you turn the key on. You don't start the car yet because I want to see the no vacuum signal, which would be a simulated wide open throttle signal. Am I making myself clear, Robert?
Yeah.
Stop playing on your phone. That's recorded too. Robert's playing on his phone.
Yes, the phone.
Yeah. If I turn the key on, is there vacuum in the intake? No. At wide open throttle, is there vacuum in the intake? No. So I got my wide open throttle reading. What do we want to see looking at a map? I see a flat line, say 4.5 volts. Start the car, I want to see that line drop down. So somewhere between 1 and 1.5 volts is typical at idle. We saw that on my case study, didn't we? On this case study, even on the bad map, there's our 4.6 at wide open throttle. There's about 1.5 at idle. It looks like a pretty good map sensor, doesn't it? The initial ranges of that, now we knew, we already went through this. We know what's wrong with it. It's a plugged hose, but that's just giving us an idea here of this checklist. How's my map? How is it operating? It's a pretty critical sensor. It looks good. We have to be careful with those numbers, though. I learned this the hard way. Well, it wasn't too hard. This Honda, look at this Honda. This is a naturally aspirated 2007 Honda Civic. 2.8 volts with the key on, engine off. And with a little bit of research, Honda calls their maps a 1-bar map, a 2-bar map, and so on. What's 1 bar? Is around 15 psi. So 1 bar would be atmospheric pressure. 2 bar would be able to read, I think, if I'm saying this right, would be able to read 15 pounds above atmospheric pressure. But notice the range of this map. It seems to me like this car was set up to use the same map sensor and computer system for also a turbo design. It looks that way to me. Why is the Honda voltage is so low, key on, engine off? It would be that. So that's pretty cool. Make sure you look up your spec. This particular map, I'm calling it analog. Why? Because an analog signal does this. What's a digital signal do? Does this. Ford, being different than everyone all the time, like to use digital map sensors. You won't see these anymore, so spending a lot of time here is not important. Digital map. So the signal, here's what's important. The signal you cannot measure with a voltmeter. Guys, look at me. Test question. Tomorrow. Can you measure a digital map sensor's frequency range, signal range, with a digital voltmeter? The answer is no. Can we use a digital multimeter set in the frequency mode? The answer is yes. These Fords will produce a signal like this. It is a 50% duty cycle signal, meaning the highs and lows are equal. The highs are 5, the lows are 0. If it's 50% duty cycle, we covered this in section 3, what does that mean about my average? If I were to hook a regular voltmeter up to this signal wire on this Ford, what's that tell me about my average? What will it read on my regular voltmeter? 0 to 5 volt square wave at 50% duty cycle. Very good. 2.5 volts. And it will not matter if the signal is 90 times per second or 160 times per second, you'll have the exact same signal. My first Ford map sensor that I looked at, I replaced it because I thought it was bad. Key on engine off, 2.5 volts. Start the van, 2.5 volts. Wide open throttle snap, 2.5 volts. I got a bad map sensor. Throw a map sensor in it, didn't fix it. Learned a lesson that day, didn't I? Cannot measure Ford map sensors because they have variable frequencies. What do we need to do? We need to shift our scale to a frequency scale so we can measure it, and then everything's the same after that. Okay? 5 volt ref, ground, same checks. The signal circuit, though, for integrity testing, see what? Which section will we talk about digital on-off signals and integrity testing? See section 2, switch inputs. In fact, one of the things I mentioned on the second page of section 2 is a Ford map sensor. Moving on. This is where I want to be the rest of the time. Map sensors. Testing them. This first line is probably the most important thing that you can ask yourself anytime you have a map sensor trouble code. You need to think about this. Map sensors measure manifold vacuum, right? Anything that affects manifold vacuum can cause a map sensor fault code. This car that we have in here, this Buick Century, and I haven't edited the video that we shot yesterday with the plugged up cat and the BAT02 sensor. Plugged up cat is going to affect intake manifold pressure, wouldn't you think? That's why the car won't run. Exhaust valve opens, we try to force this gas out and we can't get rid of it. So what happens? Exhaust valve closes, intake valve opens. Where does all that pressure go? Back in the intake. If this car had a map sensor, it doesn't, but if this car had a map sensor, we would have a map sensor trouble code on this car. And here's the thing. You scan this car, you see a map code, the first thing that you're going to say to yourself, because you know now how important the sensor is, be like, oh, I got a map sensor problem. You might, but what's the other part? What's the other half of this question? It could be the engine's running poorly, causing false map. Is that what you said? This is a false map trouble code. Guys, most of the time, when you have a map sensor trouble code, it's a false map code. You have an engine running problem that's causing it. Say a 4-cylinder engine with a 2-cylinder misfire. How well is that thing idling? What do you think? It's not idling very well. So what does the computer have to do to the idle air control valve to make the car idle at 700 RPM? Because that's what its desired idle is. It has to open it up very wide. And when we open it up very wide, what do we do to manifold pressure? We drop it. So that same car that might idle at 1.2 volts, firing on all 4 cylinders, is now idling at 1.2 volts at 700 RPM, is now idling at 2.5 volts on the map sensor at 700 RPM. Why are we reading 2.5 volts? Idle air control valve is open more, atmospheric air is in the manifold more, and what does that computer system know? It says to itself, at 700 RPM, with the TPS being at 0.5 volt, which would be idle, that's a factor in here too, it looks at TPS, looks at RPM, and it says, yo, what are you doing up there? You shouldn't be. What's it get? Map trouble code. What's wrong with the car? Oh, you're a rookie. You see a map sensor trouble code and you say to yourself, I got a map sensor problem. No, you don't. You got a bad ignition core. Waste spark system, 2 cylinders in my scenario. We have to be careful, don't we? So let's take that and let me show you another case study. And that would be, where am I? Right here. Again, I took these from my videos, guys, in that playlist. And I'm not going in order anymore, so you have to bear with me. Let me find the beginning of this. I think it's this one. Yes. Or is it this one? Okay, good. In this picture, this is my case study on a 2005 Chevy Trailblazer. You will find this on my free channel. Okay? 2005 Chevy Trailblazer. What do we see in memory here? A P0106 trouble code. We have a map sensor trouble code. Nice of Snap-on. I'm going to plug Snap-on for this to provide us with a troubleshooter. And in the troubleshooter, I learned about this, that it says that carbon buildup on the throttle body and plate may cause this code. And I'd never seen that before. This is a few years ago, the first time I saw it. And I go on a rant. You need to watch this video because I go through the whole flowchart and I compare what we find to what the flowchart says. And I went on a rant of how ridiculous the flowchart was because you would have changed parts that the car didn't need. And all it needed was the throttle body cleaned. So where in this, where's the logic that a throttle body that's dirty can cause a map code? It's kind of strange. Well, this is drive-by-wire. This is a drive-by-wire system. Let's go a little further into this. We'll cover more of this stuff in section 20 when we talk about idle speed controls. When we finished up our potentiometers yesterday, we talked a little bit about the drive-by-wire throttle body, and we said that the computer eliminates the idle air control valve. There is no idle air control valve on a drive-by-wire. The throttle plate itself is the idle air control valve. Normal throttle position angle with a clean throttle plate on these systems is under 10%. Guys, the car is idling. Once you look at these numbers, it's a little bit difficult to see. What do we see right here? Throttle angle. Desired indicated, TPIND, that's indicated angle, is 26%. Where's my RPM on this? Engine has not started yet in this picture. So, let's go to the next page. And let's see this now with the engine running. This is now at 897 RPM right here. Let's use the magic pen, because that'll disappear on its own. 897, and then throttle angle is 23%. And I think I have my map voltage here. It's 1.22 of a volt. Car is idling. Remember, this car has a map code. The fix is to clean the throttle plates. Here's the throttle plate before. And where we're looking would be in this area where we see this black ring, right? That's where we're looking. Not a great still shot there. Next page is when we cleaned it. After looking at this, we could have cleaned that a little bit better. Oh, there's still some crap in there. Clean the throttle plates. Here's the picture after the car is not running. I was just showing the map voltage, key on, engine off. How's that look? 4.65 volts. That sounds about right. No pressure in the manifold. Sorry, not no pressure, no vacuum. High pressure in the manifold, high voltage on the map. Engine's not running yet. Throttle angle is 25%. We start the car, and I'll let it run for a minute. Same RPM, we're about 800 something, so that's a factor in there too. Run time. Let me pause here for a second. Run time will change your desired idle too. Have you noticed when you first start your car that your idle is a little bit higher, even when it's hot? When you first start your car, your idle is a little bit higher for the first 30 seconds or so before it drops down a little bit lower. So these captures were skewed a little bit by that, but here's the point, guys. At 765 RPM, I'm only at 7% throttle angle now. Map voltage isn't much different, is it? It's 1.2 volts. So I agree with you that there's a question here, and why would that set a map code? You would think it would set a TPS code, not a map code. I'm not the engineer. I didn't design the program. Here's what I know. Computer's looking at RPM, map, and TPS, isn't it? Our RPM, our map, and our TPS would all be looked at. And the question is, are we at idle? I think that's how we can think of this. Computer's looking at those three sensors and saying, are we at idle? Yes or no. Now, maybe that's the wrong context going into this. Throttle angle at 25% is not a typical idle throttle angle. See, we are now. So this is one that I believe computer's thinking the car's under load off the TPS, and it's not seeing it on the map sensor. So what does it set? A map sensor fault code. Now we could argue that and say, well, but the RPM wasn't high, and I'm with you. There's questions here. That's not important. Do you understand that map sensor trouble codes can be false? And we can have some crazy stuff set map sensor fault codes. Questions on that one? Again, watch that video, 2005 Chevy Trailblazer. It's a good video. I cover the whole thing with all of it. Let's see where I'm at here. All right, the rest of this. Wiring checks, calibration tests. All of this can be handled. What's that noise? All of this can be handled with the rest of my case studies. So I'm going to end that. Let's go back to here. To give me, I don't know, give me like 15 more minutes. You guys okay with that? We'll break. Instead of coming back here, we'll go to shop. Is that cool? Unless you want to break now and I'll finish these. What do you want to do? Everybody all right? Robert, you all right? Stay with me, man. Come on. Stay focused. All right. Start up here on this one. What am I showing? What am I showing here? A GM fuel tank pressure sensor. Wait, I thought we were talking about map sensors. Well, I have a problem here. My fuel tank pressure sensor, I have a code for it, and it's 0 volts on the scan tool. Guys, by the way, this next segment, this will apply to every single 3-wire sensor on the car. No, take that back. This will apply to every single 3-wire potentiometer or pressure sensor on a car. There are some crank and cam sensors that are 3-wire that will be different testing, but those are revolution type sensors. Any pressure sensor, any potentiometer, you can follow this same thought process. My concern, it should be yours too, going into this is, do I have a wiring problem or do I have a sensor problem? That's where we're at. This is what we're trying to do. With a 0 volt signal on this tank pressure sensor, do we have a wiring problem or do we have a sensor problem? Step 2, because I did not have a data parameter to go by, you follow how that dictated my next move. My next move, I'd like to use ScanData to do my checks. Can't do it, so where am I now? I'm underneath the car. This shot was difficult. I'm underneath this truck. I think it was a truck. Doesn't matter. And I'm back probing the tank pressure sensor signal wire and reference wire. I'm double T-pinning. I know I told you not to double T-pin stuff, right? But that was primarily for outputs. I'm not so much worried about it for an input. We still want to be careful with the reference circuit, but that's just showing you hookups here. Checking wiring. Next page, next caption. I'm showing my 5 volt reference. I don't know why. Oh, got it here. This is 4.9. That says 4.99, and that says 0.01. That is the top one. This is my signal. Let me use a different color. That's pretty poor. Can't see that very well. This is maybe if I use green. Nope, that's not much better. Yellow. Whoa. It's getting crazy on here. Hang on. Where's that go? There we go. This one, that's 4.99 volts. That's this guy right here. What wire is this? What do you think? That's supposed to be a question mark. That's my reference. Remember, ScanData showing us 0 volts. Wait, it did say ScanData, huh? I screwed up there. There was a data PID. I'm sorry on this one. We started with a data PID, right? Tank pressure voltage was 0. My fault. So scratch that. Either way, we're confirming wiring. That doesn't change anything. I just misspoke on that. This is my 5 volt reference. I have one coming up where I don't have a data PID. So that's my 5 volt reference. and this one right here is my signal wire. Our signal at the sensor, so we're changing up here. Our signal at the sensor is 0 volts. The signal on the scan tool is 0 volts, but that still doesn't tell me that my wiring's good. Could my signal wire be shorted to ground? Do I have to worry about my sensor ground? Some of you might be thinking, well, what about the sensor ground? We talked about this yesterday. If you have a sensor with a bad ground, what's your signal voltage going to read on any sensor? Would it be higher than normal or lower than normal voltage? It'll be higher than normal. If I have a sensor, it's 5 volt across the resistor, and we'll make the ground be open. Signal circuits here. This is going to be 5 up here, agreed? Five volts here, and without current flow, microamp current flow, but without current flow, no voltage drop, so this is 5, 5, 5. What's the signal voltage going to read? 5 with a bad ground. I'm not worried about the ground. Based on my voltage signal. Scan data is reading 0. Signal is reading 0. What's left? We covered this in our signal circuit integrity chapter. Can't remember the chapter number, section 11 maybe. Unplug the sensor. What should it do? Potentially go to 5. If it doesn't go to 5, what are we going to do? We jump the reference to the signal. If you watch this video, I know that my 2 channels up here, my yellow and my green, are connected to the reference and signal wire individually. Watching scan data here, I disconnect these 2 leads, and I jump them together with a paper clip. What am I doing? Why would I do that?
See if the sensor's better.
Look at the scan data when I did this. You see it? What's the scan data showing right here? I went from 0 volts down here to 5 volts up here with the 5 volt reference jumped to the signal wire. Why am I doing it here instead of underneath? Just because I can't get the camera under there. Does that make sense? How's my wiring from the sensor all the way up to the computer? Do I need to use the ohm meter? Follow a manufacturer flow chart? Are we done? What's it need? Needs a sensor. 6. That's my channel. That's how to find these, again, playlists, section 8. All right, let's look at this one. A power steering pressure sensor circuit. We have a fault code. Well, I've never worked on a power steering pressure sensor before. Doesn't matter. What is it? It's a pressure sensor. How does it operate? Exactly like a map. So we have direction already. What I'd like to do, this is the one I don't have scan data on. Again, I apologize for that last one. What I'd like to do is look at that pressure sensor, this power steering pressure sensor on the scan tool, and I'm looking for a data pin, and I don't have one. I looked all over. I don't have one. So I have to change a little bit, right? The last one, what I showed you, is doing voltage checks combined with scan data. And on this one, I can't do the same thing. I need to do voltage checks alone to tell me whether or not my integrity of my wiring is faulty. So we're still dealing with either a faulty sensor or faulty wire. Now potential is here too, guys, and I should probably say this, that in light of power steering pressure, that we would want to make sure, I guess, the power steering pump was working. Start the car and turn the wheel and see if it's easy to turn. Now, that would be easy to do. So no data pin, I have to change things up. What did I do? Went down to the signal wire and I read 0 volts. That's this one. That's a flat line 0. Next image, showing the sensor wiring, 5 volt ref, signal and a ground. Probably had a wiring diagram that I was looking at. If you watch the video, it's more complete in showing that. I know which one my signal wire is. And by the way, our code was what again? Was it a low code or a high code? just says circuit fault, pressure sensor circuit fault. It's all I have. So I measured the signal, and the signal was 0. Okay? I want you to pay attention to something here. Where am I back probing this in this picture? I'm on the sensor side. Check out this picture. I'm jumping ahead. What I wanted to show is this one. Where am I connected now? I moved my T-pin from the front of the connector to the back. There's a reason I'm doing this. I'll talk about it in a second. I was a little premature in showing you that. Okay, doing some further wiring checks. My signal was 0. I need to check the rest. Agreed. In particular, my 5-volt reference. Do we care about the ground if the sensor signal voltage is 0? Probably not. Definitely not. I'm not worried about the ground. I think I show it anyway, but I'm not worried about it. What's this one showing me? Anyone? It's reading 5 volts. What wire is that? That's my reference. How's my reference voltage? Good. Could low reference voltage cause a signal voltage problem? Yes, this is basic stuff. 5-volt ref looks good. Next one. What do we have? 0, that's my sensor ground. One of the two 0 pictures was the sensor ground. I'm not sure which one. How's my ground? Good. Do we need to check the ground? No. Why? Because signal was also 0. So we're left with what? Either a short to ground in the signal wire, or an open in the signal wire, or a bad sensor. An open in the signal wire, though, we would be 5 volts here because we're measured at the sensor. If we were measured at the computer, the 0 volt signal open could be there, but because we're measured at the sensor, it would not be because of the way the circuit's designed. You follow that?
What's the easiest way to tell at first look? What one's the signal wire and what one's the reference?
Oh, that's a good question. I don't know if that picked up or not, but I'm recording, by the way. What is a quick way to identify which one the signal wire is? There's not a universal answer to that. What I would generally do without a diagram, Ryan, is I would measure all 3 wires. And based on what I see, I would make that determination. Now, in this case, I have 2 wires that read 0 volts. So I need a diagram to know. I don't want to guess, because I certainly don't want to jump a reference to a ground wire and pull a reference circuit to ground. I wouldn't want to do that. And that's why in the book, when we do integrity testing, I tell you to use a 5K ohm resistor in case you do it wrong. But as we've seen throughout a lot of my case studies, if you're following, is our reference circuits are pretty well protected. So even if you did that, as soon as you fix it, it'll go away. But I don't want to chance that. So that's one way. But then you're left with variables, which is if you have wiring problems already, that's going to hinder identification. The second one would be, this is just Ford. Ford likes to put a green tracer on their signal wires, and they've done it for years and years. So I wouldn't rely on that, but it's just another tip. Good question. Okay, so where are we? 5 volt. One of these was the signal. What am I reading here? 0. That's either a ground. Okay, I guess it wasn't exactly 0. Is this still the same car? Toyota Echo power steering. Yes. 0.22 is my signal voltage. It's pretty low. I believe on this video I would start the car, right? This is one of the things with checking these types of sensors. If it's a throttle position sensor, what do? You move the throttle plate. If it's a map sensor, what do? Snap the throttle. Look for pressure changes in the manifold. If it's a power steering pressure sensor, what do? Start the car, cut the wheel to the lock position. Is that going to give you high power steering pressure? Absolutely. What do we see? A signal change. We didn't see it. Looks like a bad sensor. We better check the wiring. This is where my T-pin's relocated, guys. I want to refer you to my signal circuit integrity chapter or the end of section 7 where I talk about this internal 5 volt resistor. You guys remember what I'm talking about? Probably not. Hang on. Come back to me. Where's Where's it at? End of section 7 would be one area. Here's what I'm referring to. Right here. This 100K ohm resistor. I'm about to use this to tell me whether or not my circuit integrity is good on this car. Why? I moved my T-pin on the backside. Why? Because I want to measure signal voltage with the sensor unplugged. Right? Signal voltage with the sensor unplugged. Where am I taking this measurement? It is certainly not on the sensor side, is it? Where am I taking this measurement? Harness side. So what do you think I'm going to do in the next picture? Any thoughts? This is the final thing. I'll be able to make a call on this if it reacts like I think it should. What's that tell me? What did I do?
Energize the.
I didn't energize anything. Remember, we're talking about an input, so we want to get that definitely out of our heads. Good thought, though. We would do that with outputs. We're doing stuff like that, section 3. The hard part about doing this, Ryan, is right now all this information's up here, but it's all spaghetti. It gets all mixed up. Eventually, you'll be able to straighten it out. Field work is key. What are we looking at? What did I do?
Throttle position sensor test. I forget what it's called.
What am I doing here compared to here? So page 14 of section 7, look at the bottom picture, and then page 13 of section 7, what am I doing? Unplugging the sensor. So in this very difficult, I'm being sarcastic here, in this very difficult diagnostic process, I have a T-pin plugged into the signal wire. Think about this for a second. I have a T-pin plugged into the signal wire. I'm taking a voltage measurement, and I'm unplugging the sensor, and I'm saying what? How's my wiring? I'm done. What does this car need? Sensor. The theory part, talking about it's difficult sometimes. Using it in the field, how accurate is this? You understand now where this 5 volts is coming from, and if you don't, you need to go back and rewatch my section 7 lectures. And if you forget there, you can go back and you can watch my section 10 lectures on signal circuit integrity testing, where we're doing this exact thing. And what do you know? There's that same picture again, and I'm talking about this. Difficult to talk about, easy to use, bad sensor. Unplug it. Done. Pretty cool. No ohm meter needed. No manufacturer flow chart needed. We're done. You guys okay? A couple more? Can you handle it? Come on, Rob. What's wrong, Robert? Huh? Come on, man. You like this stuff. You said you did. Stay with me. We did this one. You guys are in luck, right? We can skip that. This is our map with a dirty throttle body. What we got now? What's this one? A EGR flow. I have 2 more EGR flow problems that we're talking about. A pressure sensor. It's a Ford. One of them, they're different from each other, but this Ford system, they use something called a delta pressure feedback sensor, DPFE. Okay? The best thing for me to do, just so we have the right perspective here, I have this info in section 3, and I also have this info in a hardly discussed chapter because I talk about this in other places, this EGR systems. And I'm just going to refer you to this picture on Ford systems and how they operate. Guys, look. When the EGR valve is closed, the pressure in this chamber and this chamber are the same. When the EGR valve opens, the pressure in this chamber compared to this chamber will be different. Delta pressure, 2, I believe delta is 2, I think. Delta pressure or differential pressure, I've seen it listed as that too. It's measuring the difference between, okay, delta would be difference between 2, I believe, is delta. Delta time would be difference between, yeah, it's not necessarily two, but it's the difference between two. Two pressure differences. That's how the sensor operates. That's what changes the signal, okay? Let's move away from that now. It's a 5-volt ref signal on a ground type sensor. Same exact crap. We're talking about a brand new sensor. You have no idea how it works, but yet you do. What am I addressing? An EGR valve not opening or low flow trouble code. A 332. This is apparently a, I don't know why it's not listed as P0. I don't remember the year, but the name of the video, Lincoln 4.6 EGR flow testing. This is the video you guys can watch later. We have a fault code for a pressure sensor. That's where we are. What's the next step? What's the next easiest step? We're sitting in the car. I don't want to get out of the car yet. I'm lazy. Robert, we don't like to do things we don't have to do, right? Let's just stay in the car, sit there, and see what else we can play with, and see what kind of answers we can come up with. So, data pit. You got a code. Next step, look at your data, see what it shows you. What do we have? A DPFE voltage signal right here. I'm looking right here of 0.44 and 0.45. So this big spike that we see here, is that really a big spike? No, that's that Varus min-max scale feature. Basically, we have a half a volt roughly on this DPFE sensor. You don't know anything about the sensor. I'm telling you guys, that's pretty normal. Equal pressure, no flow, reading. So what's our next step? I want to check the sensor. Is there flow? You need to watch this video for more. I'm going to move past this quickly. In this image, tough to see. This is at the 7-minute, 10-second mark. I'm putting my finger over a solenoid, the EGR flow solenoid breather or air vent. And when I do that, it forces the EGR valve to open. Now, why would I force the EGR valve to open? Well, don't I need a pressure change in this area to see if the DPFE sensor works? When I force the EGR valve to open, what should happen? The engine should get real rough and stall almost, and my DPFE voltage should rise. That's what I'm looking for, okay? Watch the video and you'll get it a lot better. When I did this test, the engine, can't see my finger there, the engine, at this point the engine's getting rough and pretty much stalling, which tells me what about the EGR valve, the flow, the solenoid, all of that stuff says it's good. My DPFE voltage signal never changed. Back up, I got the wrong vehicle. When I put my finger over this port, nothing changed. There was no rough idle. I apologize. The next one coming up, that's what it's going to be. There was no rough idle, no change whatsoever in EGR flow based on sound. So how's my sensor? It's not doing anything it should be, but what makes the sensor change? EGR flow. The fact that there was no EGR flow says we don't have a sensor problem, we have an EGR flow problem. In this video case study, there's plugged up passages in the intake. Not a bad sensor, okay? You see when you're checking a sensor, it's more than sometimes just wiring. It's more than 5-volt ref signal and ground circuit integrity. It's also what makes the sensor change. In this case, it's the EGR valve. If that EGR valve never opens, pressure is going to stay the same here, and the signal voltage in our case is going to stay at 0.45. It never moves. That's not a fault of the sensor, that's a fault of EGR flow. What am I doing in this? I don't really need to show you this part. I'm showing you the vacuum as I put my finger over that. See, we have 20 inches of vacuum. That's what goes to the valve. This part, you guys can watch the video for that part. I've kind of given you the answer and what's going on. This car had, back up a page, this car had an EGR flow problem. Not a bad sensor. On this final one, is this the final one? It needs to be. I might let it break. Fine. in this one, this P0401, different car. This is 1998 Ford Ranger EGR flow testing. Guys, what are we talking about again? What's the whole point here? What are we doing? We're kind of wrapping up, if you think about it, we're wrapping up our testing methods from section 7 and section 8. I'm giving you live examples of where we apply this stuff. The text, it's in the book, you can read it. Go back, watch the lectures. This is where we're applying it. This is the most important part. I know you guys are struggling, we want to go to shop, I get it. This is the most important part of the last 2 chapters. How do we apply this stuff in a real world situation? This is what we're doing. This P0401, what do we have? Same kind of code, pretty much. Insufficient flow. Same kind of system. What do? Well, let's look at our data pin first. I see something I don't like right away. How do I know that 0.25 of a volt on the DPFE is kind of low? I don't know. I've done 100 of them. Actually, I've probably done 1,000 of these. Not exaggerating. These sensors go bad all the time. In our last case study, though, the guy that knows that, the parts changer knows they go bad all the time. He's fixed a bunch too, but guess what he probably did in our last video? He changed the sensor and it didn't fix it. And then he figured out he had another problem. See, it only takes 2 minutes of knowledge to know that that sensor's fine. No flow, sensor voltage doesn't change. Of course it's not going to change. What about this one? Well, voltage is low to begin with, so let's keep going. I do the same thing. Notice my finger's over the same vent solenoid again, or apply solenoid. I'm trying to force the valve to open, and I do that. I get some kind of change. This is blurry here. It says 0.25. I think I got a better shot of that. No, not really. 0.25 at this bottom line, right here. Goes up to like 1.3. It sits there, and this is as I'm taking it on and off. And by the way, the engine's pretty much stalling when I'm doing this. Follow my text, that's not enough, guys. It needs to be over 4 volts. I don't like this sensor. And by the way, that text I'm referring to is in section 24. When you do this test, make sure you get over 4 volts. Are we seeing that? No, we're not. We have a problem. Looks like a sensor issue. Do we just put sensors in cars, guys? Or do we check them first? What am I checking here? What did I do? Why is my DPFE voltage reading 5? What do you think I did? I unplugged it. I'm done. What's this car need? Sensor. Do you think maybe there might be a few other checks? Things like we should probably make sure that these hoses here are intact, or somebody that was not paying attention, I've seen this, reverse the hoses. There's 2 different ports. Watch the videos, you'll learn more about these sensors. I unplugged it. What are we doing now? We're done. Put a sensor in it. I go through the wiring checks anyway in this one, because what if you didn't have a scan tool? If you didn't have a scan tool, this is how you do it. Check your wiring. So I'm just showing back probing the sensor. Next image, reading 0.27. Which one is that? It's probably my signal wire. You had a question earlier. How do you know which one the signal is? Well, remember, ScannerDanner read 0.25. Actual signal is 0.27. That's probably my signal wire. Next image, scan data 0.29, just showing the 2. It's okay to be a few hundred millivolts off. Remember, we're using a different ground location most of the time than the computer's using, so voltages will be slightly off. What am I doing now? Sensor ground. Question here, did we need to do this test? What's the problem with our DPFE signal? Is it low or high? Signal's low. Will a bad ground cause low signal voltage? No, it will not. Again, am I worried about the ground? No. Should we check it anyway? If you want to, that ground is good. 0 volts on that ground. Next page. What am I doing? Just moving my T-pin down the line. That's all I'm showing there. What's that one? Hard to see that. Pretty blurry. Watch the video. What is that? 5 volts. 5 volt flat line. How's my reference wire? It's good. And then the final step would have been to, I'm back on my signal wire again, reading 0.19 this time. It's moving around a little bit, no big deal. Part of the sensor being bad. Signal's still plugged in, I wrote here. My signal, that's not signal, well, Should have wrote sensor still plugged in. Okay, back probing the sensor. What do you think my next move is? This is, and I'm done after this. This is for the guy that says, well, I don't have all your fancy equipment. I can't do that stuff. Really? You can't connect a digital voltmeter that's like $10 you bought at Radio Shack or Sears and do this exact same check that I'm doing right here? What are we doing? What's that? I'm back probing the signal wire. And what did I do? Same thing we did when we looked at scan data. I don't have a fancy $10,000 scan tool. You don't need one. You can do this with a voltmeter. Same thing I saw on the scan data, which was what when I unplugged it? 5 volts. What am I doing here? Unplugging it. Same check, 5 volts. Guys, this is a good sum up. Section 7, Section 8, and Section, which one is that? Signal circuit integrity. Section 10. Any questions? Sorry. That was long. I think it was worth it. I appreciate your attention. You guys can take a break, and then we'll go to shop.